All right, so back to number 5. Okay, so again, long division, we cannot use synthetic division because I have this coefficient of 4 up front. So in working through this quickly, we think about, okay, 4x, how many times does it go into 8x to the 4th? So I know that 4 goes into 8 2 times, and I know that I would have to multiply 8 times x cubed in order to get there. So together, again, we're talking about now 2x to the 3rd power. So now when I multiply 2x to the 3rd power times 4x plus 3, again, that's going to give me 8x to the 4th plus 6x cubed. But remember that we're subtracting this binomial, and when you subtract a binomial, you have to distribute the negative symbol all the way through. So I'm noticing the 8x to the 4th is going to cancel out, but 26 minus 6 is going to be 20x cubed minus 9x squared. We can repeat the process. So 4x goes into 20x cubed. We would say 5x squared times. Again, now multiplying. Excuse me, 20, let's see, after I multiply, 20x cubed, 5x squared times 3 is going to be 15x squared. Again, this is a subtraction problem. So when you subtract, you really have to add the opposite. So the 20x cubes are going to cancel out. The negative 9 and the negative 15x is going to be, or x squared, excuse me, is going to be negative 24x squared plus 14x. And the process continues. 4x goes into negative 24x squared. We would say negative 6x times. Again, multiplying, negative 6x times negative, negative 6x times 4x would be negative 24x squared. Negative 6x times 3 is going to be negative 18x. But again, this is a subtraction problem, so we have to add the opposites. 24x squareds are going to cancel. As for my, let's see, the 14x plus 18x would be 32x, and we're going to drop to 24. So one more time here, 4x goes into 32x, we would say 8 times. So now when I multiply, this time we're going to get 32x plus 24. Remember that we are subtracting just a little bit more space, which means that we're going to add the opposites, and we're going to end up with 0, which is great news because that means that there's no remainder. Should there have been a remainder, we just simply put the remainder over my divisor, and we'd have it. But my final answer here is 2x cubed plus 5x squared minus 6x plus 8 for that final answer. All right, so next up, let's perform the operation and write the result in standard form. Again, when we've got our imaginary numbers, again, standard form is a plus bi. Again, trying to put it in that format. So, excuse me, losing it today. Sorry about that. So for this next problem, again, when we go to work here, we're going to say 9 minus 6i. That's unphased, but I have to distribute my negative through. So minus 4. Now plus I. So please remember that when you're working with these imaginary values, or these complex numbers is a better way for me to say it, again, we can combine the imaginary portions, we can combine the real portions. So the real portions, 9 minus 4 is 5. The imaginary negative 6i plus I is going to be minus 5i. That is in standard form, so we're done. Part B, this is going to require the FOIL method. So multiplying this out, I'm going to multiply the first here. That's going to give me 2 times 3 is 6. The outside, 2 times negative 2i is going to give me negative 4i. The inside, 3i times 3 is going to be positive 9i. And the last term, 3i times negative 2i is going to give me negative 6i squared. So with that, I now need to combine my like terms. So I'm going to start by combining in the middle. And I know that that's going to give me, again, I have 6. Negative 4i plus 9i is going to be positive 5i. And we can do a little bit better than 6i, or negative 6i squared. Again, I know that I squared is equivalent to negative 1, so that's really like asking you what's negative 6 times negative 1. So, of course, we're thinking that we're going to say it's positive 6. So now when I combine my like terms, we'll end up with 12 plus 5i. So if you're wondering, well, yeah, don't we have a shortcut for that? Not in this case. Again, that shortcut exists only when you multiply complex conjugates, and those were not complex conjugates. All right, next up, kind of another variation in part C of what we did in part A. So to rewrite this problem, after distributing my negative through, we really have 11 minus 8 minus 5i plus 7i. Now that we're here, we can go ahead and combine our like terms. The real portion, 11 minus 8, is going to give me 3. The imaginary portion, negative 5 plus 7i, is going to be positive 2i. And we got it. Part D, we want to write the equation in standard form. So the only issue that we have here in part D with 3 minus I over 1 minus 3i is that we can't have an imaginary value in the denominator. So the trick here, what we've got to do to get rid of it, is I have to multiply by the complex conjugates. The complex conjugate of 1 minus 3i is 1 plus 3i. If I multiply that on the bottom, I have to match that and do it on the top. So on the top, there's really no way around it. We have to do the FOIL method. So in multiplying, again, first here, 3 times 1 is 3. Outside, 3 times 3i is 9i. Inside, negative I times 1 is negative 1i. 9i minus 1i is going to be positive 8i. And then our last term, negative I times 3i is going to give us negative 3i squared. Again, now this is all over. Remember that we have a shortcut. Anytime you're multiplying conjugates like a plus bi times a minus bi, all that we're going to get is a squared plus b squared. Again, a is the real portion out front, b is the coefficient in front of the I term. Again, simply square a and b and add them together. So in this case, we would say that a is positive 1, so 1 squared. We would say that b is negative 3, so negative 3 squared is 9. And just realized I left that as 1 squared. I think we can all handle that. Yes, that is going to be, well, that is going to be positive 1. All right, so now going about cleaning this up in the numerator. Again, we can do a little bit better than this. Negative 3i squared is really going to be equivalent to positive 3 plus the other 3 that we have is going to leave us with 6 plus 8i over, I know that 1 plus 9 is 10. So this seems like this should be sufficient, meaning that we're done, but we have to think about putting this in standard form, or we have to think about reducing these fractions. So one way that we can think about this is that in standard form would literally ask you to put 6 over 10 plus 8 over 10 I. And then to finalize this, yeah, we're just going to reduce fractions. 6/10 is going to be 5th plus 4/5 I. That will be our final in standard form. Okay. All right, so next up, let's take a look here. Before I guess get going too far, in the top left corner of your test bar, again, please note top left corner, I want you to draw a square. Then I want you to clearly shade in the top, or color in the top left corner of your square. Again, the top left corner of your square, you're drawing this in the top left corner of your paper. All right, you do that, I'll know that you watched this, and yeah, hopefully it makes some sense. All right, so back to this. We've got the function f of x equals x cubed minus x squared minus 14x plus 24. So in part 7, it says to use Descartes' rule of signs to determine the number of positive and negative zeros. So the number of positive zeros, hopefully we recognize that's going to be a little bit easier. All we have to do is look at f of x and find our sign changes. So we went from positive to negative, stayed negative, changed positive. So with 2 sign changes, anytime there's 2 sign changes, that tells me that there will be 2 or 0 positive real zeros. So positive real zeros. All right? When it comes to finding the negative real zeros, a little bit more work involved. I have to actually find f of negative x, which means that I rewrite my original function of x cubed minus x squared minus 14x plus 24. But everywhere that I saw an x originally, I have to put negative x and then reevaluate and see what the signs are going to be. So I know that if I take negative x and cube it, I'm going to end up with negative x cubed. If I have negative x squared, that's going to become positive, but times the negative up front is still going to be negative x squared. Negative 14 times negative x is going to give me positive 14x, and then the plus 24 constant is not adjusted at all. So now that we have f of negative x, now I'm going to evaluate my sign changes. So from negative to positive, stays positive. So this tells us, kind of running out of space here, that we will have exactly 1 negative real zero. All right, So we know that there's exactly one negative real zero. We know that there are 2 or 0 positive real zeros. Maybe I should have mentioned this at the very beginning of the problem. That since there's a degree of 3, that means that we're going to find 3 total zeros. So if there's 3 total zeros and we actually land on, or if we hit on the fact that there's 2 positive and 1 negative, there's all 3. But if there are 0 positive and 1 negative, that tells us then that there has to be 2 imaginary zeros that are out there. So in number 8, we want to list all the possible rational zeros. So this is asking now to do the f of x, or I'm sorry, the p over q. Excuse me, I don't even know what I'm talking about. So our p-values here, they're going to be, again, looking at the factors of positive 24. So here we would say plus or minus 1, plus or minus 2, plus or minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, and plus minus 24. The q values, we're looking at the lead coefficient, which is positive 1, which its factors are only plus or minus 1. So when I put the p over q's, they're not going to change. That's what I'm trying to say. So if this is my list, realizing what we did, of course, is that we started with an infinite number of possibilities, and then we just narrowed it down to a much more manageable list of, looks like about 16 here. So now at number 9, when we want to actually find the zeros, we have a much better chance at doing so. We're going to go ahead and give this a shot here. Looking, when I say give this a shot, I'm talking about synthetic division. So synthetic division, I'm going to go ahead and set this up with my my coefficients of 1, negative 1, negative 14, and positive 24. All right, so we've got this P over Q list. I don't know where we want to begin. Maybe I don't know, 3. Let's try that. I'm sure I'm a horrible actor, so you're seeing right through this. So if I were to drop the 1, now multiply 3 times 1 is 3. Add straight down, we're going to get positive 2. Multiply 3 times 2, we get 6. Add straight down, we get negative 8. Multiply 3 times negative 8 to get negative 24. Oh my gosh, it worked. Oh, it's exciting. So we ended up getting the fact that x is equal to 3. Okay. So we got that x is equal to 3. That's great news. We can keep on moving, right? Let's go ahead and test another value. I don't know. Negative 4. Let's try negative 4. So think about my remaining list here. Now, I wasn't thinking about my remaining list. I've got x squared plus 2x minus 8. For some reason, in the back of my mind, I was thinking this wasn't going to factor, but upon looking at this again, it's absolutely going to factor. So I don't know why I had in my mind that it wasn't going to. So if I were to factor this in the traditional way, thinking about what multiplies to negative 8 but adds to 2, hopefully you're thinking about positive 4 and negative 2. So once we factored it this way, now we're going to find our last 2 remaining zeros. Again, if I set x plus 4 equals 0, I now know that my root or 0 is going to be x equals negative 4. If I set x minus 2 equal to 0, now I know that x is equivalent to positive 2. So if we were tasked with finding all of the zeros, again, we've done exactly that now. My zeros, they'll be located, again, x equals negative 4, positive 2, positive 3. All right, moving along here. Next up, you can see that we actually have the exact same function, I believe. We're just continuing on here. Now we want to figure out the maximum number of turns. So this is going to stem from the fact that the degree is 3. And if the degree is 3, that tells us that there could be up to 2 turns. The way that we find that, of course, is that we look at the degree minus 1. It's as simple as that. For the max number of zeros, again, if the degree is 3, the maximum number of zeros is going to be 3. Again, your degree is equivalent to the maximum number of zeros. Now, the beginning and the end behavior, now, again, degree being 3, that's odd, tells us that we're going to be going in opposite directions. My lead coefficient is still positive 1, so I'm essentially going to be following the same pattern of my cubic function. So for that reason, we could answer that on the left end, we're going to be falling, but on the right end, we're going to be rising. That's written up. Last, we want to go ahead and draw the graph. So I need to stop the podcast here. I'll draw the graph when we start the next one. But again, all that we're going to do is keep in mind this end behavior, keep in mind our zeros and multiplicity, and we'll be in good shape.